Welcome to section 2.3 where we're looking at techniques for computing limits, and this is going to be more of our analytical methods versus looking at graphs and tables to determine what the precise limit is going to be of a function at a certain value. So I've always said that the first rule of limits that you need to try when attempting the value of a limit is to plug the a value in. So plug a in is kind of the first rule of thumb that you have to do. So if you end up getting a value, then that's your limit. If you don't, then you end up having to do some other techniques in order to figure out what that limit is. And we'll see those later on. But first we're going to look at some properties of some basic limits, and starting with the most basic with a constant. Say if I have the limit as x approaches a of some value c, that is going to be just at that constant. Think of it, I have a horizontal line. There's no other value that it can be besides that constant. For instance, if I say I want the limit as x approaches 0 of 5, if I were to graph that y equals 5, it's a horizontal line at y equals 5. When I approach any value along there, it is always going to equal 5. The next one is our identity property. So if I'm approaching a for x of x, that was our identity function, y equals x, then I'm going to plug that a value in for x, and I'm going to kick out an a. So for example, if I have the limit as x approaches negative 3 of x, I plug that in, and the value I get is negative 3. For an exponent, if I have the limit as x approaches a of some x value to the nth power, x squared, x to the 7th, whatever the case may be. Again, I'm going to plug a in for x. As x approaches a goes in for x, then I would have a to the n power. So for instance, if I said I want the limit as x approaches negative 2 of x squared, I'm going to plug negative 2 in, and I get to square that. So in the end, my ultimate answer here would be 4. And finally, our linear function. The linear in the book, it gives us as the limit as x approaches a of f of x. Well, if I plug a into that, then I get f of a. But if it's linear, remember that I can write that in terms of mx plus b. So it would be like ma plus b, where I'm multiplying the slope times the a value and adding the b. So for example, I know sometimes those ambiguous cases are a little bit strange, but if I see a tangible or a valid line here, an example, it makes it a lot easier. So I'm going to take this a value and plug it in for x and figure out what that value is. So I get 5 times negative 1 and add 3 after that by the order of operations. Therefore, this is equal to negative 2. Multiply, you get negative 5. Add 3 gives us negative 2. Okay? So those are kind of your basic properties. Plug in that a value in, see if you get a value out. But we also have some that end up with different operations within a function and such. So how do we handle that? So I'm going to assume that limit as x approaches a of f of x equals L, and that the limit as I approach a of g of x equals m, that they exist. They have valid numbers, L and m. The following properties hold true where c is a real number and n is going to be greater than 0 when we use n, possibly as a power, and n greater than 0 is an integer, so any positive or negative whole numbers there, okay? So we have some different constant multiple product, quotient, power, and root. These are the ones that we're going to look at, and so basically for the sum, I look at the limit as x approaches a of f of x plus g of x. Sum means to add. So if I'm adding two functions together, therefore by these properties it tells me that I can in a sense separate each one of those and find the limit of each one of them individually. So in a sense somewhat distributing that limit symbol, but don't get too caught up on that because that's technically not mathematically correct. But I can end up then taking the limit of f, which was L, and adding it to the limit of g, which was m. So I can just add the two limits together. Likewise with the difference. So instead of having now a sum between them, I have a subtraction between them. By this property, it tells me that I can take the limit as x approaches a of f and then subtract that from the limit as x approaches a of g of x. And so if we do that, we're going to take each one of their values and subtract them together. So it's not necessary that you write these out individually. It's necessary that you know that it's capable of happening to be able to do that individually. Okay, that would be just way too much writing. Although some people might want to do that. All right, what if we have a constant multiplier, which means that I have some c times f of x? Well, that is going to be the same as pulling that c kind of out front and multiplying it by the limit as x approaches a of that f of x. And so what happens in that case, since the limit as x approaches a of f of x is L, then I would just be able to multiply c times L to get my answer for that limit. Okay? A product of two functions for my limit as x approaches a. This time we have f of x times g of x. Notice whenever that is written that there is no symbol between those, so it symbolizes multiplying. So we can actually then individually take the limit as x approaches a of f of x and multiply it by the limit as x approaches a of g of x. And because f is equal to L and the limit of g is equal to m, then that means that I can just end up multiplying that L times m to figure out the limit. Okay. The next one is a quotient. Quotient is the answer to a division problem, so therefore we have f of x divided by g of x. And we can, it is true that we can individually divide the limits. Sorry for the delay again on here. So I could take the limit, squeeze it in here because it's going to get really tight, of f of x all over the limit as x approaches a of g of x. And so technically, like before, all the ones before, we can take that L and divide by that m. Now, guaranteed that here that m is not equal to 0, because if that's equal to 0, we have a problem with that fraction. All right, so a power then would be something that looks like if I'm taking a function to a power. So we had x to the n in the previous properties, but here I'm taking a function to the n power. And so this can be the same as taking the limit as x approaches a of f of x and taking all of that to the n power, which then symbolizes that because that limit as x approaches a of f of x is equal to L, then I can just take L to the n power, and that would be my answer for that. And finally, this will give us the root. And so a root, if you remember, like a square root is 1/2, the cube root is 1/3. So we're going to write it as a fractional exponent, that the limit as x approaches a of f of x to the 1 over n power. That's going to symbolize our root. Means that we can take the limit as x approaches a of f of x to the 1 over n power. And again, since that limit as x approaches a of f of x is equal to L, then that constitutes that I can just take L to the 1 over n power. Okay? So those are our properties, and just so you know that they are valid to be able to be done, doesn't mean that we write them out each time. So again, mathematicians, once you know kind of the rule, it's always nice to be able to do the shortcut. And so we'll see that here with a lot of these. So if I give you 3 limits here, the limit as x approaches 2 each time of the function value of f is 4, of g of x is 5, and h of x is 8. And so we're going to kind of put those together using our properties, which again, I can rewrite this as the limit as x approaches 2 of f of x minus the limit of x goes to 2 of g of x all over the limit as x goes to 2 of h of x. That's technically what we're doing, but remember, we can just take the L minus the M and divide by that value. So in this case, the limit as I go to 2 of f of x is 4. Then I would subtract the limit as we go to g of x, which is 5, and divide that by the h of x limit as x approaches 2, which is 8. And from there, I can just simplify that value as a negative 1/8. So we don't want to make it too hard, but here it's going to be just some math from there. All right, trying this one. I have 6 times f of x times g of x, and then add h of x to that. So I'm going to plug these in here. 4 is equal to f, 5 is that g of x, and 8 gives me that h of x. So I get 6 times 4 times 5 for the first 3, and then add on to that 8. Therefore, let's see, this is 20 times 6 is 120 plus 8. Therefore, my limit as x approaches 2 of that function or combination of functions is 128. Finally, I need to find that limit of that g of x function, and I'm going to raise that to the third power. So what is that equal to? It's equal to 5. So I can kick back that this is 5 to the third power, which is 25. So as long as you know those rules, this becomes pretty easy, just plugging some things in. Again, plugging that a value in is important. So let's try this with polynomials and rational functions. Okay, so if I end up throwing in the a value to each one of these, in a sense it's like we're evaluating that function value at a. So if I plug 4 in for every x that I see for this function, I need to do 2 times 4 cubed minus 5 times 4 squared plus 3 times 4 minus 10. And so, from here, it's order of operations. It's not calculus. That was the calculus part. So here, I'm going to cube 4, which gives me 64, times 2 gives me 128, minus 4 squared is 16 times 5 is 80, plus 12 minus 10. So then if you subtract 80, we get 48, add 12 is 60, subtract 10, this value becomes 50. And it's a valid number, so you're good. Move on. And this rational function, I'm going to plug 2 into every single place that I see an x. So I get 3 times 2 squared minus 4 times 2 all over 5 times 2 cubed minus 36. So what does that become? Hopefully we get a valid number. We don't have to go any further. 3 times a 4 gives me a 12 minus 4 times 2 is 8. All over 2 cubed, 2 times 2 times 2 is 8, times 5 gives me a 40 minus 36. So it looks like we have a 4 over 4, which equals 1. Valid answer for a limit, therefore, that is our answer. And we can move on to this radical function that we have here. Again, plugging a in, that's the first rule of limits. Try to plug that in. I get underneath that square root, 2 times 2 squared plus 9 plus 3 times 2 minus 1 all over, don't forget the denominator, 4 times 2 plus 1. So here, I would simplify underneath that radical first. So this gives me 2 squared is 4 times 2 is 8 plus 9 is a square root of 17. Unfortunately, 17 is a prime number, so we wouldn't be able to break that down. Then I have plus 6 minus 1, so I'm going to combine those as a plus 5. And then all over the denominator, this gives me an 8 plus 1 gives me a 9. Now, nothing here can be simplified. It doesn't look very pretty, but that is a valid answer for our radical function that we have there. Okay? All right, very good. So that's the rule of plugging a in. Now, what happens when a is plugged in and you cannot get a valid answer? You may end up with something like 0 over 0 or 1 over 0, which we know that with fractions is very invalid. You can't divide by 0. So in order to take care of that, one must make use of factoring and rationalizing with conjugates to evaluate the limit. So we're going to evaluate this limit, and this limit, if I were to plug 2 in, then I end up with a 2 squared plus 4 minus 8. Well, that's 4 plus 4 minus 8 is 0 all over 2 squared is 4 minus 4. So this gives me 0 over 0, which is not a valid answer. So we have to do something with our function to be able to work with that. So I'm going to go back, and since I have a polynomial on top and bottom, I'm going to think about factoring these. So if I factor the trinomial on the top into two binomials. Last sign is a minus, so they are different inside, so I need an x plus and an x minus. What do we multiply to get 8 that we subtract to get a positive 2? Well, it must be a plus 4 and a minus 2. Now, once I have that, then I'm going to factor the bottom as an x plus 2 and an x minus 2 because that is one of those difference of squares. You must know how to factor a difference of squares and be able to recognize it very easily. So that's very nice because if you look at these two factors, those are the same. So I'm going to cancel them out, basically making the limit as x goes to 2 of x plus 4 all over x plus 2, my new function. So hopefully that when I plug that 2 value in, that I don't get 0 over 0 this time. That gives me the 0 over 0 that I just eliminated. So when I plug 2 in, 2 plus 4 is 6 over 2 plus 2 is 4. That gives me a nice valid number. It's a fraction, but that's okay. Final answer here would be 3/2. So if we now turn to this rational function, I guess you could say, I have a square root of x minus 1 and then an x minus 1 on bottom. This is where we're going to kind of symbolize the rationalizing. So when you're rationalizing functions, in college algebra, algebra 2, you had to deal with conjugates. Conjugates are basically, in a sense, an opposite of a two-term binomial. So if I have square root of x minus 1, then square root of x plus 1 is its conjugate. So that means that you're basically just changing the sign of the sign between them. So anytime, first let's try, if we plug in 1, what do I get? I get the square root of 1 minus 1 over 1 minus 1. And when I do that, I do get 0 over 0 again. So we have to do something. We just can't plug the a in. So this is an exercise in doing it by rationalizing. So I need to, and sometimes you have to rationalize the denominator, sometimes you have to rationalize the numerator. So wherever the radical is, let's find the conjugate of that expression. So that's going to be the square root of x plus 1. Remember, just change the sign between them. But if I multiply the top by that, then I must also multiply the bottom by that. Because technically this is a 1. I'm not changing the function itself. I'm just changing the way it looks. So when I simplify on the top here, as x goes to 1 for our limit, now make sure you rewrite these. I don't know if you've noticed that. I rewrite this each time. Don't be lazy and just work with the function because it doesn't make sense to just drop that limit notation. So on the top, that means I need to FOIL these conjugates. So if I do my first term, square root of x times square root of x is the square root of x squared, which is just x. The outside would be a plus root x. The inside is a negative root x. That would cancel themselves out. This, in a sense, is a difference of squares. So then the last term is a minus 1. Now, that's very good because look what was in the bottom. That's an x minus 1. So we're going to force a cancellation here to get rid of that idea of 0 over 0. So if I have this x minus 1 in the bottom, along with this square root of x plus 1, these two terms that are exactly the same, the x minus 1s, are going to cancel themselves out. That eliminates the idea that I get that 0 over 0. So now I reduce down to the function where I have what's left over of 1 over the square root of x plus 1. And now I can plug a in. After I modify that function, I'm going to plug 1 right in here, and I get 1 over the square root of 1 plus 1. Well, square root of 1 is 1, plus 1 is 2. Therefore, my valid answer for this limit is 1/2. And if you were to graph that, you would be able to see that as well. Okay? All right, moving right along. Here we get into some one-sided limits according to some piecewise functions, and also to this function. We'll see it, that again a little bit. So to see again, remember the limit from the left and the limit from the right must be the same for this limit to exist. So we'll check that out. And all of those rules above apply to one-sided limits as well. We still want to plug a in to see if we get a valid value. If not, then we use another technique in order to get a value for the limit. So let's look at this piecewise function. Our first request is to find the limit as x approaches 1 from the left. Look at your inequality. 1 is that break point. And so is this the inequality that has all the numbers coming from the left of 1, or is this the inequality? Well, that means x is greater than 1, so that would be coming in from the right. So we want to hone in on this inequality for this problem right here. what you need to do is you need to take that a value. This is the a, there's the a also, and plug that into the function of the region at which you are coming to the left of 1. So that means I need to plug 1 in for the x, and I get negative 2 times 1 plus 4. This gives me negative 2 plus 4 is a positive 2. So that's the limit as we approach 1 from the left. Now, as we approach 1 from the right, for my inequality, for all numbers greater than x, we are approaching that value from the right. So again, I need to plug a into that function. So I'm going to go the square root of 1 minus 1, which actually gives me a 0. And then for my last request here on this function, what is the two-sided limit from the left from the right? These two things must be equal. Notice they are not. Therefore, this limit does not exist. So it's a possibility for you to have limits that don't exist. Okay? All right, so let's move this page up a little bit. Okay? If I were to look at this a value of 2, right now when I plug 2 in the bottom, I'm going to get a 0. Okay? If I plug 2 into the top, this becomes an 8 minus 2 squared is 4 times 24. Plus 2 times 8 is 16. So that's also going to give me a 0. So this is a function where we have to end up doing a little modification of that. So I'm going to try the factoring. I don't see like a conjugate here to where I could kind of cancel some stuff out or to exchange that. Anytime you have like add or subtract with radicals, that might symbolize that you have to do the conjugates and rationalize. I'm going to try factoring first because a lot of times that's going to help out. Notice that there is a common x up there, and so I'm left with x squared minus 6x plus 8. All over, I'm going to write this as x minus 2 to the 1/2 because that is my fractional exponent. Now I'm going to keep factoring this trinomial. So I have an x, and so that's going to go down to 2 binomials. The sign is the same, so they are, the last sign is a plus, so they are the same that match the first, a minus minus. I need an x in there. What do we multiply to get 6? What do we multiply to get 8 that we add to get 6? Well, that's going to be a 4 and a 2. Now, I'm all over that x minus 2 to the 1/2. Now, I can go ahead and put 2 in, but because of these two factors right here, I'm still going to get that 0 over 0. So I need to work with these and be able to cancel. Now, notice here that's actually a power of 1. I could cancel a 1/2 into 1 by subtracting those exponents of common bases. So what's going to happen is that I'm going to cancel this into this and leave me with 1/2. 1 minus a 1/2 leaves me with a 1/2. And so my final function that I want to look at for my limits to plug 2 in is this guy right here. X times an x minus 4 times an x minus 2 to the 1/2. And so now I can plug a into my new modified version. So that means I have 2 times 2 minus 4 times 2 minus 2 to the 1/2 power. And so notice, now I don't have any fractions, so I don't have to worry about the 0 in the denominator. But this is 2, this is negative 2, and notice this is 0. Well, 0 to any power is going to be 0. Therefore, multiply across here, my answer is 0 for the left. When I plug 2 for the right in, what happens? I get the same exact values. I get 2 times a negative 2 times a 0. So again, this one is also equal to 0. Hence, the limit from the right and the limit from the left are equal, making my two-sided limit equal to 0 as well. And that right there gives us our values kind of on some one-sided limits of using some factoring and being able to work with a piecewise function as well. Okay? All right, so we got 2 little sections to go in this chapter, or in this 2.3 section, I believe it is, in which we are going to go over the squeeze theorem of how to find a limit of something that could be pretty nasty, and also some trig limits, where we could use some identities to change our function up a little bit. So the squeeze theorem states this, and we're working with 3 functions here, f, g, and h, that satisfy a certain inequality, that the f values are less than or equal to the g values, which are less than or equal to the h values for all values of x near a, except for possibly at a. So remember, you don't have to equal at a. We just have to be close to that. Now, I'm going to kind of draw a picture of this. Okay? here's my axes, and I'm going to draw this function here and call that f of x. And I'm going to hone in kind of around this a value. Okay, I'm going to change my pen color. I'm going to end up drawing a function that looks like this and call this y equal to the h of x function. And so basically this inequality holds that the f values are smaller than any g values that are smaller than the h values for every single value that we have. So I'm going to come in here and do a g function, okay? Maybe I end up having something that looks like this, and maybe I even kind of squiggle around or something like that. But in every single case, the h is the biggest, the g is in the middle, and the f is the smallest. So you can see that all the way through for all those values. So a situation like this would be what we are working with on what we call the squeeze theorem. So what does the squeeze theorem say? The squeeze theorem basically says that if the limit as x approaches that a of the smallest function is equal to the limit as x approaches a of the largest function, and that is equal to some value of L, then it holds true that since this inequality holds true and these two limits are equal to L, therefore the limit as x goes to a of that g function is also equal to L. So a lot of times you'll see this, and like I said, some nasty functions that you have. And most of them do include a trig function, okay? Now the trig functions are kind of nice because here I have x squared times the sine of 1 over x. So there is a property for the sine function. If you remember the sine curve, what it looked like graphically, it ended up doing this and it kept bouncing back and forth between 1 and negative 1. So sine has to be restricted between 1 and negative 1. So we can write an inequality like this. Now, I'm going to say let theta equal 1 over x. So I'm going to plug 1 over x in, and now I get this inequality of negative 1 less than or equal to sine of 1 over x, which is less than or equal to 1. Now, what am I trying to do? I'm trying to get that function in this inequality. Now, I'm close. I got this part. Now I need to get this part because that is a product, and I have a compound inequality. That means I can multiply this by x squared, multiply this by x squared, and multiply that by x squared, which becomes negative x squared less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. Now, what do I have here? I've got three functions, okay? I'm going to let this one symbolize f of x. This is the g of x that I'm looking for, and I'm going to let this one symbolize h of x. So what I need to do by the squeeze theorem is to determine what is the limit of f and the limit of h. Is it the same value? And if it is, then I found the limit of g. So I'm going to say, okay, what is the limit as x approaches this a value of 0 of my f function, which is negative x squared? Well, that's one I can plug the a in. 0 squared and the opposite is still going to be 0. What now is the limit as x approaches that 0 of the largest function? And that function is just x squared. So when I plug 0 in and square it, I also get 0. So therefore, these two limits are exactly the same. And because of this inequality where f is less than or equal to g, which is less than or equal to h, then I can conclude by the squeeze theorem that as x approaches 0, of that x squared times the sine of 1 over x, that will also be 0. And that's your answer by the squeeze theorem. Okay? All right. Last two problems are dealing with trig functions. And whenever I deal with trig functions, again, there are some identities that might come into play to be able to change that function around. If I try to plug a in here, what do I get? I get the sine squared of 0 all over 1 minus the cosine of 0. So 0 is on the axes. This is the point 1, 0. Remember, this is the cosine value, that's the sine value. So the sine of 0 is 0 squared, which is 0, all over 1 minus the cosine value is 1. So I get 1 minus 1, therefore I get 0 over 0. That's a problem. We don't get a valid answer. So we're going to either have to change this function somehow to get that valid function. Now, by an identity, if you remember, there's the sine squared of x plus cosine squared of x equals 1. And so a lot of times when you're dealing with sine squares and cosines, this comes into play. So if I want to solve for sine squared, that's the same as 1 minus cosine squared of x. Now, that's kind of nice because I look and I have a 1 minus cosine of x in the denominator. Now, why is that kind of nice? It may be in disguise, but notice if this is a function, I can factor that because it's a difference of two perfect squares. So we have that a squared minus b squared when I factor is an a plus b times an a minus b, which we've seen before. So I'm going to go ahead and factor a trig function, and that's okay. 1 minus cosine of x and 1 plus cosine of x. And the reason that that's awfully nice is because if we recall what's in the denominator, I have a 1 minus cosine of x, which can eliminate those two factors, eliminating the fact that I get 0 over 0, and now I can take the limit as x goes to 0 of 1 plus cosine of x to get my valid answer. So I'm going to plug in that a value of 0. So I get 1 plus the cosine of 0, and if you recall, on the unit circle, the cosine of this 0 degree angle is at 1. So this becomes a 1. 1 plus 1 is 2. That is my final answer for that limit. Okay, so you might need to brush up on some of your trig identities as well. All right, last one. We have a double angle within there. The double angle formulas for sine is 2 sine cosine. The double angle for cosine, the easiest one is the cosine squared minus sine squared, but there's some other variations of that. So, why do I proceed that? Well, I'm kind of getting the horse before the cart here. If I plug in 0, what do I get? I get 1 minus cosine of 0 all over sine of 0. Why am I talking about those identities? Because this cosine of 0 is 1, so 1 minus 1 is 0. Sine of 0 is 0. Therefore, I have to do something, okay? So I'm going to change this cosine of 2x, and I'm going to change it to the identity of cosine squared minus sine squared. So I get 1 minus cosine squared of x minus sine squared of x all over a sine of x. And what you try to start with first may not work, so you may have to try something else. And so when I simplify the top a little bit, I get 1 minus cosine squared plus a sine squared. So let's distribute that negative basically first. So I end up getting 1 minus cosine squared of x here and here when I distribute that negative through. Then we're going to get a plus sine squared of x all over sine of x. Okay? Now, looking at this, you got to try some things. So hopefully you can, from the last problem and this Pythagorean identity, can kind of recognize what this piece is here. That 1 minus cosine squared is also going to equal a sine squared. So again, rewrite your limit symbol. Don't be lazy on that. I'm going to exchange that 1 minus cosine squared for a sine squared of x plus the other sine squared of x. Whoops, there we go. All over the sine of x. Now, I have two things on top that I can combine together like terms. So I'm going to get the limit as x approaches 0. Sine squared plus sine squared gives me 2 sine squared of x all over sine of x. Now, why is that important? Because now I have a sine on top, actually 2 of them, and I have a sine on bottom, so I can actually cancel one of these with that square. Okay, so when I cancel it, then I end up with 2 times the sine of x. And so as x goes to 0 of 2 times the sine of x, this is kind of a new modified function that I have. And so when I have 2 times the sine of x and I try to plug in, that's supposed to be an equals, let's say, plug in the 0, then I get 2 times the sine of 0. Well, I'll go back on our unit circle. The sine of 0 is 0. Times that 2. Ultimately, for all of that work, I get a limit that equals 0. And that right there is the finish of our section 2-4 or excuse me, 2.3, and then we are going to move on to 2.4, which will include some rationalizing and a little bit more of some of our limits, where we are actually going to limits at infinity, or infinite limits. So we'll get to talking about that as we further our knowledge about limits. So until next time.